Class, in our second video passage, which is part 2, we will focus on two hypothesis tests, two t-tests. One t-test has to do with testing the correlation coefficient, that is testing whether or not x and y are linearly related. And then the second t-test has to do with testing whether or not x can help to predict y. In our context, since we've been doing an example that has to do with predicting exam grades or exam percentage based on the number of hours of study in the week before the exam, then the two t-tests would be: one, whether or not hours of study and exam percentage are linearly related, and the second hypothesis is whether or not hours of study can help to predict the mark that you will get on the exam. So these are two t-tests. So let's do those. All right. So the first one we'll do is a t-test for rho. So we have a t-test for correlation coefficient rho. Notice I did not use R because R is the sample correlation coefficient. We don't do a hypothesis test for a sample statistic. We do a hypothesis test for a population parameter. All right, and so the test is for rho as the population parameter. So essentially, we want to show that there is a linear relationship between x and y. So that would be our alternate hypothesis. So our null hypothesis would be that there's no relationship between them. HO, HA, it would be rho is equal to 0. That there's no linear relationship, but that rho is not 0 means that there must be a linear relationship between x and y. So that's essentially what we are looking at. Let us do this test at a 5% significance level. Let us test whether or not hours of study and exam percentage are linearly related. So we'll start off with hypotheses, which I've already stated, but we've got to put it in words and then symbols. So we have hypotheses. This is 1. HO, HA. So hours of study not linearly related to exam percentage, and then of course hours of study is linearly related to exam percentage, right? So that's the statement of the two hypotheses. So let us put that mathematically, which I've already done just prior to this. So it would be HO, if they have no linear relationship, it would be rho is equal to 0 versus rho is non-zero. All right, so that's step 1. Step 2, let us frame the test statistic. So it is a t-test, so our test statistic is going to be a t statistic. Number 2, test statistic, and that is t observed is sample R minus population divided by the standard error, and the standard error of R is 1 minus R squared over degrees of freedom n minus 2, not n minus 1, but rather n minus 2. The degrees of freedom in this case is n minus 2 because we have two variables. We have x and we have y. And so therefore we have n minus 2 degrees of freedom in this situation. Whenever we're dealing with simple linear regression, that's what we have. So that's 2. 3, our decision rule. So the decision rule is a two-tailed test. If you look at the hypotheses, it's a two-tailed test, and so therefore we will have to split alpha over 2, 0.025, alpha over 2, 0.025. Now our degrees of freedom is 10 minus 2, which is equal to 8. And so therefore our critical value will be t alpha over 2, which is 0.025, 8. That turns out to be 2.306 if we look it up in the table. And so therefore this is negative 2.306, positive 2.306. And in terms of the critical value approach, if the t value is greater than 2.306, we reject the null hypothesis, or if the p value is less than alpha. I'm going to move this out of the way a little bit. And so we will write, if the absolute value of t0, observe, is greater than or equal to 2.306, or if the p-value is less than or equal to 0.05, we will reject the null hypothesis. So that is the decision rule. Otherwise, we fail to reject HL. Otherwise, fail to reject the null hypothesis. All right. So that is indeed step 3. Now step 4 is just the analysis. All we got to do is to substitute values in the equation that we have. Let's use a clean page for that. So we have T observe, which is step 4, the analysis. T observe is, remember, R minus rho. R was 0.7705. Rho will get a value of 0, which comes from the null hypothesis. HO, rho is equal to 0. And then we divide by square root of 1 minus R squared, 0.7705 squared, divided by n minus 2, which is 10 minus 2. And that turns out to be 3.42. So that's a test statistic right there. Now if we want a p-value would be, because it's a two-tailed test, so p-value is twice the probability of t exceeding 3.42, which is our sample value. And if we look at the t-table under 8 degrees of freedom, we will not actually see this value of we will not see the value of 3.42. We'll find a value that's smaller than that, and at that point it turns out that the area in the tail is 0.005. Okay, so this portion right here will be less than 0.005, because the largest value in the t-table under 8 degrees of freedom is, I think, 3.3 something. Which means that if we keep going to get to 3.42, we will end up getting a value that is less than 0.005. And if we multiply less than 0.005 by 2, then it becomes less than 0.01. So that's our p-value right here, less than 0.01. And then step 5, the decision, conclusion. So we'll say since 3.42 exceeds 2.306, that's applying the critical value approach, or since the p-value is less than 0.05, we will reject the null hypothesis. What do we conclude? We have sufficient evidence that exam mark and hours of study are linearly related. That exam percentage and hours of study are linearly related. Cool, that's the conclusion. So, can we be wrong? Of course, possibility of type 1 error. We have a possibility of type 1 error here. And the risk of type 1 error is less than 0.001. So, possibility of type 1 error, okay, risk of type 1 error is less than 0.01, and that's that. So we have evidence that those two things are related. Now we're going to do a second hypothesis test, which is a t-test for beta 1. A t-test for beta 1. So we could actually answer that very same question we just answered a while ago by asking the question, is there evidence that hours of study helps to predict the exam mark? In other words, if it did not, it should not exist in the equation. So you will get exactly the same answer, because it is not possible to have a linear relationship between hours of study and exam mark, but somehow hours of study does not help you to predict the exam mark. That doesn't make sense. The two things have to be consistent. If exam hours will help to predict my exam mark, it means that there's a relationship between those two things. And so we'll do a t-test for beta 1. So t-test for the slope beta 1, the slope. All right, so the question in essence is, does hours help to predict exam mark? So let's write that down. And we're going to go to the bigger screen. So does hours of study help to predict exam percentage? So if we look at the equation that we just, the regression equation, the population one, B0 plus beta 1x. Well, if hours x does not help to predict y, x should not be in the equation, and the only way for x not to be in that equation is for beta 1 to have a 0 value. But then if x is going to contribute to y, then beta 1 cannot be 0. It has to have a non-zero value. And so in essence, we will be testing HO, beta 1 is equal to 0 versus HA, beta 1 is not 0. All right, that's what we'd like to prove. So let's do this. So 1, our hypotheses. And we'll test at the same alpha value so that way we can compare the results. So hypotheses, HO, HA. So hours helps to predict hours of study, helps to predict exam percentage versus hours of study. So it does not help. If it's HO, we should say it does not help. My bad here. So it does not help to predict. Help to predict exam percentage. Hours of study helps to predict exam percentage, right? So consistent with that would be HO, HA, beta 1 is equal to 0 if it does not help, but if it helps, beta 1 is non-zero. So that's the first thing. 2, test statistic. So it's a T. T observed is our sample value minus the population. But we know that beta 1 in the null hypothesis is 0, so we could actually remove beta 1 from that equation, but that's okay. Leave it there, it looks okay. And then we want the standard deviation of the errors divided by the square root of SSX. Now, I'm not giving you a formula yet for the standard deviation of the errors, but I'll do that now. Standard deviation of the errors essentially looks like this. It's the square root of SSE over n minus 2, which is the sum of the squared errors over n minus 2. Now, how does that look like a standard deviation formula? If you see where it came from, sum of squared errors was sum of y minus y hat squared. So y minus y hat is an error. If I square it, that's a squared error. If I add it all up, because it's the sum of squared errors. When I divide by n minus 2, sorry, not n minus 1, because we have n minus 2 degrees of freedom, that's the variance of the errors, and if I take the square root of that, it's the standard deviation. But we refer to the numerator as SSE, which is the sum of squared errors. And we do have a shortcut formula for that sum of squared errors. Turns out that SSE can be found using the following formula. SSY SSXY squared over SSX. And we're going to need that formula a little later on in our calculation to find SSE. And then of course we have SE is just square root of SSE over n minus 2. And we already calculated SSX from earlier, SSY and SSXY from part 1. If you go back to our video part 1, you will see that. So now let's go to step 3. Step 3 is our decision rule. And it's the same decision rule that we had before. It's a two-tailed test. If we use the same alpha value, so alpha is 0.05, degrees of freedom is n minus 2, which is 8. So therefore this becomes rejection region. Negative 2.306, 2.306. The same values that we had before. All right, because we have same alpha value, same degrees of freedom, t.0258 when we divide it up by 2. So just to remind you, this area right here will be 0.025, and this area right here will also be 0.025, which is alpha over 2. All right. And so, squishing this to make a little space, we have if the absolute value of our test statistic is greater than or equal to 2.306, or if the p-value is less than 0.05, reject the null hypothesis. And then we will conclude HA. Now let's go ahead and do step 4, the analysis. So we need to calculate SE, but before we can find SE, we need SSE. So let's start off with SSE is equal to SSY minus SSXY squared over SSX. SSY is 2258.1, 2258.1 minus, and then we need SSXY squared, 631.6 squared, 631.6 squared over 297.6, and that gives us SSE. Let's see if we could find what the value of SSE is. When we divide that, that's 977.66. 977.66. Then SE, the standard error, or the standard deviation of the errors, would be, remember, the square root of SSE over n minus 2. In this case, it is the square root of 977.66 divided by 10 minus 8 gives us 10.71. So that's the standard deviation of the errors. And so now we can find T0, which is beta 1, which was 2, not beta 1, but B1, our sample value 2.122, minus beta 1, which is 0, over SE, which we just calculated, which is 10.71, divided by the square root of SSX, 297.6. And guess what? It gives us exactly the same t-value, because the two tests are equivalent. If x and y are linearly related, then x helps to predict y. That is the crux of it. And so p-value, we already know how to do that. P-value is twice the probability of t greater than or equal to 3.42, which would be less than 0.01. In case you're wondering again, how did I get that? If you actually look up 3.42 in the t-table, under 8 degrees of freedom, the area that corresponds to that would be less than 0.005, because at 0.005, the t-value is only 3.3 something, which is smaller than 3.42. So if we keep going to get to 3.42, then the area in the tail must be less than 0.005. And when we multiply less than 0.005 by 2, when we double that, we get less than 0.01. So that's our p-value right here. And then we could end with step 5. Decision conclusion. So since p-value is less than 0.05, reject HO. We conclude we have sufficient evidence hours of study helps to predict exam mark. Good. And here again we could say that we have possibility of type 1, which we already did mention. Possibility of type 1 error. All right, there's a possible type 1 error, and risk of type 1 error is the p-value, which is less than 0.01. And we're done. So those are the two hypothesis tests that we can do if we are dealing with simple linear regression. All right, so just to recap very quickly, what we did was we said we had two questions that we want to have answered through hypothesis tests. One question looked at whether or not the hours of study is linearly related to the exam mark. And that's basically, since we say linearly related, what measures that for us is correlation coefficient. So in essence, we are testing whether or not the correlation coefficient is non-zero versus it is 0. So we'll assume that is 0, that there's no relationship, and we look at the sample evidence to see if it is strong enough to reject that and conclude there is indeed a relationship. Secondly, we could repeat that test now by asking the question, does hours of study help to predict your exam mark? And the answer to that question will be dealt with through a hypothesis test. In this case, we get exactly the same answer, and that's largely because we have just a single independent variable. So if x helps to predict y, then x and y must be linearly related. And so we got exactly the same results. All right, good. So on that note, that's hypothesis testing within regression. In our part 3, we will talk about interval estimation, and that will conclude for us regression, simple linear regression. See you in video number 3.